Okay, well, again, I'm at UCSC. I'm also a contractor working with the NSRO crew. They do a lot of work on analyzing disk images, analyzing their files, and for my UCSC work, this is my thesis title, because I'm currently working on my PhD. It's overly fantastic, overly complicated, overly impressive. Software signature generation from sequential digital forensic analysis. The sequences there are sequences of disk images relating one disk image to another, because these are virtual machine states that I'm analyzing. And I've taken some steps on each of these virtual machines. I know what the inputs are, and I've seen what has changed between each of these steps. The bedrock of all this analysis of the file system differencing is digital forensics XML. So I'm going to tell what half the room at least knows already some of it. DFXML, if you don't know the story or the apocryphy, it's originally by Dr. some people. And it was originally created because he was teaching sleuthkit training classes. Sleuthkit is a way of analyzing disk images, and basically you would use it to weed through the deleted content and extract files, look for interesting hidden areas. And there's all these in and outs that you had to know. And by the time you have to say that, hey, so if you want to do a workflow with sleuthkit, first you run these 3 commands and pipe them through grep. And once you say you're piping commands through grep, you know something has gone horribly wrong. You know you're not where your analytic capabilities need to be. So he took the ins and outs that you need to know about sleuthkit and put it into an XML format. So it's a document language, DFXML is. And there's some Python bindings and other language bindings that I'll go through to let you actually do some analysis on just the XML. So you can do storage system analysis without having to need a copy of the disk image in hand or even on the same server. You could just have the metadata manifest. That's what DFXML is all about. It's a thorough enumeration of all the file system metadata. The file metadata, the file systems, the partitioning systems that organize them. It enumerates everything there that can be put into some normalizable form. Then you can do some statistics or some sort of workflow on just the XML content. There's everything you'd expect from an inode. There's a little bit of content summary in file checksum, so you can also extract the files and run plugins on them. Frequently, there's a request for antivirus scans to run these files, and you can just store that in a big long XML stream. You get to know where the bytes of a file or any of the alternate streams of the file's bytes may live on the disk. And there's also tags for provenance, which in curation I imagine you'll care about since you have very long, complicated, human-involved workflows. DFXML is about automating the forensic analysis. It's not so much about, and it's about letting people be able to run the same steps later if they need to. The tags in DFXML started out pretty specific to NTFS because sleuthkit had a lot of specializations there. But it's generic enough to run on any file system from this year, this decade, the previous decades, or 3. If you want to know more about the language and its entire specification, it's encoded in an XML schema right now. That's available on GitHub. References for all this, by the way, are going to be at the end of the slide, so you don't need to write down URLs or anything. You can just ask me for the slides and have to provide them if they're not being provided already. The schema documents all the elements, and it also happens to function. You can pipe it through XML lint and take a DFXML document you made yourself, maybe with your own generator, and say that, yeah, this is valid DFXML structurally. So DFXML is the document language. It's like HTML. It doesn't actually have live running stuff in it. So there are programming languages bindings that let you either create or read, or now both at the same time, DFXML document. The C bindings that Professor Garfinkel wrote are it's a C library you can plug into programs. The HashDeep family of file hashers currently uses those. He also wrote an original set of Python bindings called DFXML.py. It would let you read the file system objects, but wouldn't let you manipulate them because of how it was storing the data structures. And it also had you chop up your code into callback functions and run it on the behind-the-scenes hidden stacks interface. So For these reasons, because that's a matter of aesthetics. If you want to have a callback function in your code, I saw a need for writing a different set of bindings that could also let you generate a stream of DFXML as in-memory objects instead of having to write text and then write a Python program to read the text. It seems a little backwards to try to do that. So there's this set of objects bindings that you do read-write objects. I've used this to implement DFXML generation in previously existing file parsers in Python. And it follows the XML E-tree interface, which has this really nice function called iterparse. It's memory efficient. It lets you just throw away stuff once you're done analyzing. So there's emulation of that interface within the objects bindings. So that is the bedrock code on which my research lies. Most of my research code contribution has been in file system differencing and file system difference analysis. We're currently on the second revision of the original differencing algorithm because it's not straightforward to take two states of a file system and say what's new and what's changed. You would think it's just a simple set construction either way and then a set subtraction. But when you start dealing with deleted content and files that have multiple names, legitimately have multiple names, you have a lot of weird corner cases that you need a non-straightforward algorithm to follow through. The original general differencing strategy that we published was in DFWS now 3 years ago, to take two file system states or just their metadata manifests and say, here's what's changed. You could abstract that one level higher to say, okay, these two manifests could represent anything. So we needed to do a project analyzing the Xbox 360. We didn't have a working parser or any of that, but we saw this random looking code on GitHub that I could probably do it, but we didn't know how correct anything that we downloaded or anything we wrote would be. So we also took the sleuth kit, modified it. We took other codes and started implementing DFXML generators, implemented a comparator, and that told us just how incorrect each of those were because it identified everywhere that the tools had discrepancy. If you need to write a file system parser for something that you found from the 80s, then you may want to be able to test it. And this is a version of N-version programming. Have a couple of different implementations of this file system parser. You can see if you're missing anything in any of them, because they're all going to have their own bugs, I guarantee it. And all that translated to the current research, which is in analyzing the Windows registry, developing software signatures from everything that has changed and added from step to step. It was kind of straightforward to do that because the registry acts like a big, hideous file system. Now, more relevant to the curation needs I mentioned, there's a couple scripts that have been implemented and could be implemented, but the implementation is going to depend on who complains that it doesn't exist yet. So if you have a complaint that doesn't exist yet, please pass it on, and that makes it much easier to write. There's the redaction script that Simpson originally wrote, and Cam has been putting some work into that. And I believe it's on the agenda to discuss this week what's going to be happening with it. Lets you take a disk image and actually cut away some of the original bytes in case you need to remove something for public distribution. This is a way that Simpson released some of the disk images that were like entire Windows operating systems, and they could run if you didn't cut away some of the executables. So cut away the executables, it says it can't run, so I'm not violating copyright, right? No one's complained yet. There's another helper that I found handy, a user space file system that just represents disk partitions as big virtual files, because we found that if you want to just analyze a file system, you don't want to have your code analyzing the partitioning system at the same time. It just gets unnecessarily messy. Now, for further implementation, I've been wanting to write this file system that takes a DFXML metadata manifest, which represents all the file system, and just treat that like a file system itself. So you could run find, you could run grep if you wanted to, on all of on it like as though it were a live mounted disk. But this depends on people asking for it to exist. So these are references if you would like them, and that was all the time that I allotted for. And I think under a minute I'm good.
Yeah, terrific. Thank you. Thank you.